Hello everyone, welcome to lecture 9 of this course on nonlinear and adaptive control. In the last class we were discussing adaptive controllers for plants where there was an external disturbance, and we saw that classical adaptive controllers are not robust to such external disturbances. So, that it leads to a phenomena of parameter drift where the parameter estimates are not guaranteed to be bounded, which is undesirable for any control system application, because you do not want any signals in your system to be growing unbounded. And in fact, we also saw that resulted in our control input going unbounded, which is in fact disastrous. So, in the last class we did two robust adaptive control designs. One was dead zone modification and the other one was sigma modification, where we showed that by modifying the adaptive law in a suitable way, we were able to ensure that the parameter estimates they stay bounded, and of course, the tracking error is also bounded. With these two laws, we were able to guarantee boundedness of all the signals, including the control input. So, in this class, we will continue with our robust adaptive control designs. We will do the E mod or the E modification, and we will also start the projection based adaptive control design. So, we will start off with the E modification design first. So, let us go back to the sigma mod design that we had done last time, and if you remember, this was the modification term that we added, and we call this as the sigma modification term. And what this term did was that this provided the required damping, which resulted in k x hat and k r hat to remain bounded. So, we were able to show using Lyapunov analysis that these parameter estimates they stay bounded. So, there are some limitations associated with the sigma mod term, which researchers found out. So, one of them is that when the tracking error becomes very small. So, for example, let us look at this k x hat dot equation. So, when the tracking error E becomes very small, we see that the first term becomes very small, and k x hat dot is dictated by the second term, which is a sigma mod term. Okay. So, remember that sigma mod is added to ensure that the parameters stay bounded. So, its main role is to robustify the adaptive laws, whereas the first term is our main learning term, which is trying to learn the ideal value of k x hat. So, ideally we would want that the first term dominate and the second term is just in case the parameters try to drift away, they make sure that the parameters stay bounded. So, in the case where the tracking error becomes very low, we see that the second term becomes dominant, and that results in k x hat converging towards 0. So, which is something that we refer to as the unlearning phenomena. So, unlearning is when k x hat has already learned some value, some estimate for k x, and at that time the tracking error becomes very low, and so the k x hat is updated based on the second term, which makes sure that k x hat converges towards 0. So, whatever value it has learned, it basically has to unlearn that. So, this is of course not good if we are looking for good performance from our adaptive laws. So, to prevent this, another modification was proposed, which is called as the E modification or the E mod. So, here So here, in addition to we slightly modify the sigma mod term, and we use the tracking error norm, this, and also so I think there is a small error with this one. Okay. So this was the modification which was proposed. So if you look at the second term, the sigma mod has now been modified, and there is the norm of the tracking error which is now multiplied with the second term. So that is the only modification, but the slight modification results in both these terms becoming small as the tracking error becomes small. So it intuitively you could think that this would prevent the unlearning behavior and result in better performance. So let us see if we can prove stability using this E modification term. Of course, if you simulate, you should be able to see some performance improvement using the E modification term as compared to the sigma modification term, because intuitively it seems that the unlearning phenomena would be curtailed. Okay. So, let us go back to the Lyapunov stability analysis and see if we can prove stability. So, we will use the same Lyapunov function candidate. Okay. And we follow the same steps that we had previously, and we end up we take the time derivative, and we end up with this expression. Minus sigma r norm of E k r tilde square plus sigma x norm of E. So, by the way, these norms are all Frobenius norms. This is the Euclidean norm of the tracking error vector. Okay, so then we have kx tilde f, and then we have this. If you remember, we had this residual term in case of sigma mod as well, but here we have the tracking error multiplied with this. Okay, so this is the expression that we get once we substitute for the error dynamics, and also these update laws for kx hat and kr hat, which have been modified using E mod. Okay, the task here is to see if we can prove stability still. So so here we see that we can further upper bound V dot like this, and then this disturbance term also we can upper bound that by using the upper bound of the disturbance. So, plus lambda max which is the maximum eigenvalue of the matrix P times d bar times norm of E. D bar is the upper bound on the disturbance. Okay, and then we have so let's also collect similar. So let's move this term at the end, and let's have the negative terms in the beginning. So that just helps us uh, in figuring out what terms are negative and what terms are positive, so that we can dominate the positive terms with negative terms. So let's collect the negative terms together. Okay, so these are the negative terms, and then we have the positive terms. One which is associated with sigma x or kx, and the other one which is associated with kr. And of course, we have the disturbance term as well. Okay. So now we see that there is a set of negative terms which are given by this, and then there is a set of positive terms which are given by this. So if we can somehow under some conditions, of course, if we can somehow dominate these positive terms with our negative terms, then we can show that B dot is less than or equal to 0, which is the desired objective. But if not, then under some conditions, if we can say that these negative terms dominate these positive terms, then we can try and work on those conditions and see if those are reasonable, and we are able to prove stability. Okay, so what can we do with the positive terms? So we can use the Young's inequality again. So we had discussed that last time. So using the Young's inequality on terms like this one. So we say that this is less than or equal to norm of kx tilde by 2 plus norm of kx. Oh, the tilde is not there on the kx here. Yeah. Okay. Similarly for kr tilde. Okay. So using these upper bounds, we can further upper bound v dot as minus lambda min square minus sigma x. So these are good terms. These terms are our friends, and we have to kind of eliminate the positive terms using these negative terms somehow, if we can do it. So now we use the Young's inequality here and separate out these two terms. So we'll have sigma x norm of E kx by 2 plus sigma x over 2 e kx square plus sigma r over 2 norm of e kr plus sigma r over 2 norm of e kr plus, of course, we have the disturbance term. Okay, so now what we can do with this is that we can combine some terms like this one and this one we can combine, and then we can combine these two terms, and what we end up with is simply, so I can in fact now, so if you combine these two terms, what we will get is minus sigma x over 2 of norm e times norm of kx tilde square, and similarly for this term. So and then we can take norm of e outside and see what we get. So we hope that we would be able to prove that v dot is less than equal to 0 under some conditions. So let's see what those conditions come out to be. Plus sigma x over 2 kx tilde square plus sigma r over 2 kr tilde square minus sigma x over 2 kx square minus sigma r over 2 kr square and minus lambda max of p times d bar. Okay, so this is where we end up with. So now what can we conclude from here? We can conclude that if the term in the brackets is positive, then we can say that v dot is less than equal to 0 and all signals are bounded and we are done, right. So so for the case that this term in the brackets is positive, we don't have a problem, because v dot will be less than equal to 0. We can prove the signals are bounded. But what if this is negative? So what we can say is that let's try and put this in writing here, that v dot is less than equal to 0 outside the set, let's call that as pi, and we define that set as e kx tilde kr tilde such that this term in the brackets is less than equal to 0. So we can write that as lambda max of q over 2 times norm of e plus, so let's collect the terms which are dependent on the states, kx tilde plus sigma r over 2 kr tilde. So we'll have squares here, right, and then that is less than equal to the constant terms, which is sigma max of times d bar plus sigma x over 2 of kx square plus sigma r over 2 kr square. Okay. So, what we see here is that this set is compact, that is that inside this set your if the trajectories are inside this set, they are trapped. They the tracking error E is also bounded. The parameter estimation errors are also bounded because the sum of these is less than equal to some constant. So, this is some constant, right. So, once the trajectories are within this set, then your tracking error, your parameter estimation errors are all bounded, and outside this set V dot is less than equal to 0, which means that you can say that the trajectories again are the tracking error, the parameter estimation errors are bounded. So, for all time we can say that E of t, k x tilde of t and k r tilde of t are bounded. Okay. So, this set is a compact set. Let us just mention that here. So, if you start outside this set, then we know that V dot is less than equal to 0, which means, so since V is positive and V dot is less than equal to 0, we can say that the that V is bounded, which means that E is bounded and k x tilde is bounded and k r tilde is bounded, and once the trajectories enter this compact set, they stay within this set, because when they try to go outside, V dot will be less than equal to 0. So, all right. So, what we can say is that the errors are all bounded. So, which is what we are looking for, right. Okay. So, using the E mod, we have been able to ensure that all the signals are bounded, and heuristically or intuitively you also see that it prevents unlearning. So, I will encourage that that you can that you should simulate an adaptive controller with sigma mod and adaptive controller with E mod, and compare the performance of the two controllers and see for yourself if you see that E mod performs better than sigma mod, especially in the region where the tracking error becomes very small, because that is where the unlearning happens in sigma mod. Okay. So, so this was another robust adaptive method. Now, we move on to the projection modification. So, both sigma mod and E mod modification terms, they add a damping term to the adaptive laws, which result in slow convergence, because they try and damp the learning rate of the adaptive estimates k x hat and k r hat, and as a result the convergence may be slow. So, for fast adaptation, we would like that as much as possible we adapt based on the gradient descent update law, which is given by the Lyapunov analysis, and only when the parameters we feel are trying to drift away, that we constrain them. So, this is where this projection modification scheme is used. So, it is mostly going to provide you fast adaptation, because it does not have the damping terms that are there in the sigma mod and the E mod modification terms. Okay, so the basic idea is that we need to assume that our actual parameters, they lie within a bounded convex set. So, we will see how convexity helps us here, but the idea is that we want that the actual parameters, say theta, it lies within a convex bounded region. And so let us for a moment use kx here, because we are used to kx and kr. Okay. So let us assume that we know a region. We do not know the exact value of kx, but we know that it lies in this convex bounded region, right. And if we know that, then we would like to start our updation process somewhere within this set. So, we would like to start kx hat of 0. So, at time 0 we would like kx hat to be within this set, and then kx hat of course follows the adaptation law, which is the unmodified law, which was initially given by the Lyapunov analysis. It is also the gradient based update law. So, it then tries to update based on the adaptive law, and it does that continuously. So, there is and as long as it is within the convex set, we use the same adaptive law. However, when it reaches the boundary, that is where we see if a condition is satisfied, and that condition is that if at this point, which is the boundary of the of this convex set, is the derivative, that is kx hat dot, at this point, is it pointing outside of this convex set, or it is pointing inside the convex set. So, for example, if it is trying to if it is pointing outside the convex set, we will try and limit it to stay along the boundary of the convex set. So, we apply a projection. So, we project the adaptation such that it stays along that along the tangent. Okay. However, if it at this point the derivative is pointing inside, it just means that at the next instant kx hat will go inside the convex set. So, and stay bounded. So, it is only when the estimate is on the boundary of the convex set and it is pointing away from the set, that we try and project it on the tangent plane, such that it either stays on the boundary of the convex set, or it later moves inside. So, we do not want these estimates to move out of this set, and that is how we make sure that these estimates always stay bounded, and we also do not have any damping term that sigma mod and E mod terms have. So, you could use fast adaptation gains, high adaptation gains here. You could do fast adaptation as long as the estimates are on the boundary, and on the boundary pointing outside, that is when they are modified. Okay. So, what we can say is that using projection, the parameter estimates are constrained to lie inside a bounded compact set in the parameter space that contains the unknown parameter. Okay. So, now if you remember, we did similar modification in the indirect adaptive control. So, there the task was that the the parameter estimates had to be projected in a region away from origin. So, we did something very similar. We projected the estimates such that they are always away from the forbidden region, right. So, it's very, this approach is also very similar to the projection modification that we did in the indirect adaptive control case. The only difference here is that we have to construct a convex set where the actual parameter lies. So, that knowledge has to be assumed that the actual parameter actually lies within this closed bounded region, and then we only do adaptation within this region. So, that is the basic idea. Okay, so, here as I mentioned, that the assumption that we will have to make is, say that the actual parameter is within some bounded region. So, k x and k r, which are the actual parameters, they are upper bounded by k x bar and k r bar, and these two are known constants. So, this is one limitation, one drawback as compared to, say, E mod or sigma mod, where we do not assume any such assumption. In fact, in dead zone also we do not assume the upper bound on these unknown parameters. There we assume that the upper bound on the disturbance is known. So, you see that all these 4 methods that we have covered so far, they have different flavors, different assumptions, and it depends on the application which one you want to use. Okay. So, we move on and see how this projection modification can be used to design adaptive controllers. So, before that we will do some preliminaries which will be useful for us. Okay. So, the first preliminary is first definition is a convex set. So, a subset omega, which is a subset of R n, is convex if for all x y which belong to omega, we have that lambda x plus 1 minus lambda y belongs to omega, where lambda is between 0 and 1, where 0 and 1 are also included. So, so this just means that if a set is convex, then you take any 2 points in that set, and the line and all the points on the line joining the 2 points will also lie within the set. So, that is what a convex set is. Definition 2, a function f from R n to R is convex on R n if f of lambda x plus 1 minus lambda y is less than equal to lambda of f of x plus 1 minus lambda of f of y for all x y in R n. Again, lambda is between 0 and 1. So, what this means is that let us illustrate that using a graph of a function f. So let us say the graph is something like this, and this is the point x, this is the point y, and f of x is this, and this is f of y. So this function is convex if all the points on the line joining x and y, so which is denoted by lambda x plus 1 minus lambda y. So all this region is basically denoted by lambda x plus 1 minus lambda y. So as we change lambda, we get these different points between x and y. So if the f of lambda x plus 1 minus lambda y, which is basically this this curve here, this segment here, this is less than equal to lambda times f of x plus 1 minus lambda times f of y. So which means that now if we look at the line joining f of x and f of y, which is this line, so this line should always be greater than equal to this this curve, which is true in this case. So we say that this function is a convex function, whereas if you look at a function like this, and this is x and this is y, so and if we try and join the line between these 2 points, so it wasn't a very good. Okay, let me try and do this again. So this line, of course, is not greater than equal to this curve here, right? Because there is a portion which is greater than this line. So this is a non-convex function. Okay. Okay, so we move on. So let us look at lemma. So this is all under preliminary stuff. Lemma 1. So let there be a function f which is defined on Rn to R. Let this function be convex, and we just did the definition of a convex function. So let this function be convex. Then for any constant delta which is positive, the subset gamma, which is defined as omega, which is defined as, let's call it omega delta, defined as theta belongs to Rn, and f of theta less than equal to delta. Okay, so this is how this set omega delta is defined as. So if this function f is convex, then this set is a convex set. So the proof is not very hard to follow. So we what we need to show is that this set omega delta is a convex set. So which means that if we take any 2 points within this set and we construct a line joining these 2 points, and if all the points on this line also belong to this this set, then we say that this is indeed a convex set. Okay. So let us consider 2 points. So let theta 1 and theta 2 belong to omega delta. What this means is that f of theta 1 will be less than equal to delta and f of theta 2 will be less than equal to delta. Okay. So, now we use the information which is given, which is that this function f is convex, which means that f of lambda theta 1 plus 1 minus lambda of theta 2 is less than equal to lambda f of theta 1 and plus 1 minus lambda f of theta 2. Okay. So, we know that this is true, and then we use here the fact that f of theta 1 is less than equal to delta and f of theta 2 is also less than equal to delta, because theta 1 and theta 2 are points in the set omega. So, then we can further upper bound this by lambda delta plus 1 minus lambda delta, and we simplify this, and the lambda delta terms cancel and we are left with delta. So, what we are looking at is that f of lambda theta plus 1 minus lambda theta 2 is less than equal to delta, which means that lambda theta 1 plus 1 minus lambda theta 2 should belong to this set omega delta, right. Now, since theta 1 and theta 2 belong to this set omega, and the line joining these 2 points, all the points on that also belong to this set omega, we conclude that omega delta is a convex set. Okay. So, now we move on to lemma 2. So, in case you are wondering why we are doing this preliminary stuff, we can think of it as some lemmas which will help us when we do our stability analysis later on, to prove that the projection based modification, wherein you have to construct a convex set, leads to stable design. So, so far we have done the definition of a convex set and a convex function, and we are also doing some properties related to convex function and convex sets. So, this will just help us when we do our Lyapunov analysis later on. Okay. So, so lemma 2 says that let there be a function f of x going from R n to R let this function be differentiable and convex, and for delta greater than 0 we consider the subset omega delta, which is constructed similarly, which is where the element belongs to R n such that f of theta is less than equal to delta. Okay. Now, let us consider a point theta within this set omega delta such that f of theta is less than delta. So, what this means is that this point theta is actually an interior point, because we are saying that f of theta is strictly less than delta. So, we exclude all the points which are on the boundary. of the set. So, it is an interior point of the set omega delta. Okay. So, let us consider another point and let us denote it by theta b, which belongs to gamma delta. So, it is again a point in the set gamma delta such that f of theta b is equal to delta. So, what this means is that this point theta b is actually on the boundary of the set omega delta. So, theta b lies on the boundary of the set omega delta. Okay. So, what we have done is we have considered a convex differentiable function f, and we have constructed a convex set omega delta, and we have considered 2 points within that set. One is in the interior, so it cannot be on the boundary, and the other point theta b is on the boundary of the set. Okay. So, now we are making a statement. So, this lemma makes a claim, which is that theta minus theta b transpose gradient of f evaluated at theta b is less than equal to 0. Okay. So, remember theta and theta b are elements in R n. So, it is a vector, and that is why we use this transpose, and the gradient of f is basically partial derivative of f with respect to theta evaluated at theta b. So, this is very similar to a dot product. So, if you look at this carefully, it is basically a dot product of two vectors theta minus theta b and the gradient of f evaluated at theta b, and we say that the dot product is less than equal to 0. So, just to be clear, this gradient of f at theta b is in fact a vector, a column vector and theta 2 and so on till del f del theta n evaluated at theta b. So, I guess this was, let me just write this again. Assuming that the vector theta goes from theta 1 to theta n. Okay. So, pictorially what does this lemma say? So, what this means is that suppose we consider a convex set let me make this. So, we consider a convex set, and so let us call this as the set omega delta. Okay. So, on the boundary of the set we say that f of theta equal to 0, and on the interior we say that f of theta is less than equal to delta, right. So, let us consider this point theta b, which is on the boundary, and let us consider a point theta which is in the interior. Okay. And theta minus theta b will be this vector which is pointing towards theta. This is the vector that we are referring to as theta minus theta b. So, we take the dot product with gradient of f. So, the gradient of f will be the normal to this level curve, right. So, if you draw the normal to this level curve at this point theta b, this will be the gradient of f at theta b. Okay. So, now if we take the dot product of these two vectors, we will see that it comes out to be less than 0. So, this is what this lemma says, that if you have a convex set and you consider 2 points, one on the boundary and the other one on the interior, and we construct a vector joining these 2 points, then the dot product of this vector with the gradient of the function f evaluated at the point on the boundary will be less than or equal to 0. So, let us go ahead and prove this. So, intuitively we see that it makes sense, but we need to also prove this mathematically. So, since the function f is convex, so what we can say is f of lambda theta plus 1 minus lambda theta b is less than or equal to lambda f of theta plus 1 minus lambda f of theta b. So, this basically comes from the definition of the of a convex function. So, then we manipulate this equation slightly, this inequality slightly, and what we end up with is f of theta b plus lambda of theta minus theta b will be less than or equal to f of theta b plus lambda f of theta minus f of theta b. Okay. So, this is what we get. Okay. So now we take this f of theta b to the other side and we divide the inequality by lambda, and what we get is f of theta b plus minus f of theta b less than or equal to, so we divide this by lambda and we get f of theta minus f of theta b. Now, since the points theta and theta b, they belong to the set omega delta. So, we know that, of course, it is also given that this is less than delta and this is equal to delta. So, when we take the difference, it will of course be less than 0. So, we can say that f of theta b plus lambda theta minus theta b minus f of theta b divided by lambda is less than or equal to 0. Now, we take the limit lambda tends to 0. So, we take the limiting case, we take the limit so what we get is limit lambda tends to 0 f of theta b plus lambda theta minus theta b minus f of theta b by lambda is less than or equal to 0, 0. So, what does that so this remind us? So, as an aside, this is very similar to saying that limit h tends to 0 f of x plus h u minus f of x. So, this is the definition of the the directional derivative, so which is the derivative or the gradient of f dot with u. It's also sometimes written as gradient of uh, del u f, which is same as saying that f is, this is a directional derivative f of f taken in the direction of the vector u. So we basically it's basically the gradient of f, and we project it onto the vector u, and that's what this this expression is. Okay, so we use this for the expression that we got above, and what we can say is that this is equivalent to gradient of f evaluated at theta b dot with theta minus theta b, and that is less than equal to 0. So this is so dot, you can write this in matrix vector notation, and it basically boils down to theta minus theta b transpose gradient of f of theta b less than equal to 0. So which is what we had set out to prove, that this vector dotted with the gradient of the level curve, or the normal to the level curve, is always going to be less than equal to 0. So that's where this convexity property comes into play, and we'll see how this lemma will help us in proving the stability in the case we have a projection modification. Okay, so in this class we have finished the E modification, which is heuristically said to be better than the sigma modification term, as it can prevent unlearning and we can still prove boundedness of all the signals. Then we moved on to the projection modification based adaptive laws, where we want to constrain the parameter estimates to lie within a bounded convex region, and whenever they try to move outside, we project them back. So we did some preliminaries which will enable us to write these projection modification laws for the MRAC case. So we will finish that in the next class. Thank you very much.